guys, we're going to start a very new topic today in our series, and it will be kinematics of machinery. So before starting the topic, I want to ask you one simple question: what is kinematics? So before dealing with kinematics, every one of you have almost done the study of motion. So while studying the motion, there are two aspects of it. One is the force, and one is the acceleration and velocity. So force is the cause of the motion, and acceleration and velocity are the outcomes of it. So whenever we deal with the acceleration and the velocity analysis of it, we are dealing with actually kinematics. And whenever we deal with the force and the cause of the very motion, then we call it the dynamics. So in this entire series, you are going to learn about the kinematics of machinery, that is the velocity and acceleration analysis of every kind of system that you are going to deal in the mechanical world. So guys, let's start with link and nodes. What is link? Link is one of the most basic thing in kinematics of machinery. So starting with the definition of link, I will say link is that part of a machine which has some relative motion with respect to another part of a machine. So for example, let's take this marker in my hand. This marker has some relative motion with respect to my right hand. So this thing has a relative motion, you can see it well. So this is a link. Now let's go on to nodes. What is node? A node is a junction or a point about which the link actually has its relative motion. So for example, in my case, if this marker is having a relative motion about my fingers, so this finger, this particular area we'll call as node. So for example, if this is a link and it is attached to some other link over here, this circular thing is called as a node, because this link is free to rotate about this link, about this point. Okay, so it's called node. Now on the basis of the number of nodes present in this link, we will classify the link into many parts. I have written 3 parts here because we generally consider and will deal with only 3 of these links, but you can actually go on with many other links. So the first classification is unary link. So let's suppose the link, our link has only one node, so we'll consider it as unary link. So for example, if this marker is only fixed to my one hand and it is having relative motion about this one hand, so we'll consider it as unary link. If the same marker is attached to both of my hands and it is having a relative motion about both of my hands, then we'll consider it as binary link. So binary link basically has 2 nodes, and for example, ternary link has 3 links. It has 3 nodes. So if a triangular system is there and it has 3 nodes over here, and one link is attached here, one link is attached here, and one link is attached here, all these links are free to move about these nodes, and this is considered as one link because it is shaded. So this link is called as ternary link because it has 3 nodes. So you can also go with quaternary link, you can also go with pentanary links. So depending on the number of nodes, you can actually move on. So guys, now let's start with kinematic pairs. What is a kinematic pair? A kinematic pair is a system of 2 links having relative motion between them. So in our previous example, this marker and our hand, the system formed a kinematic pair. Now we can classify kinematic pairs into various categories based on the relative motion between them. So we have divided the kinematic pairs into 5 categories here. So it's sliding pair, turning pair, rolling pair, screw pair, and spherical pair. So let's begin with sliding pair. What is a sliding pair? A sliding pair is basically a pair of 2 links wherein one link actually slides through the other link. So the best example of the sliding pair will be a reciprocatory engine, where the piston actually slides through the cylinder. So that will be an example of the sliding pair. Now let's move on to turning pair. Turning pair is actually nothing but where one link revolves about another link. So the example is, suppose it's a pivot here. Now it is one link is attached to this. So it's a node in this case. So this link is turning about this point, pivot point. So this is an example of turning pair. Now let's move on to rolling pair. So anything that rolls on a surface is called as a rolling pair, because for example, let's say the gears rolling on another gear, or you can say a wheel that is rolling on a ground surface, so it will be a rolling pair. Now let's see the example of screw pair. A screw pair actually considers both the motion, translational motion as well as the rotatory motion. So whenever a screw is rotated, it also proceeds with the translatory motion of going in. So this system is called as screw pair, and spherical pair actually is nothing but a ball sorted mechanism. Everyone must have seen that ball sorted mechanism, where there is an enclosure and inside it is a ball. That ball is free to rotate about it, and so it's called a spherical pair. So guys, let's move on with the another type of classification of kinematic pairs. Now we classify the kinematic pairs based on the type of contact between them. So it is basically classified into two broad categories: higher pair and lower pair. So what's higher pair? Higher pair is basically that kinematic pair wherein both the links have only a line or a point contact between them. So for example, if a wheel is rolling on the ground, so at any moment of its contact, only a line is in contact between them. So it's a higher pair. Or you can say a ball bearing on a surface. So at any moment of its operation, only a point is touching with the ground. So it is a higher pair again. Now let's move on to lower pair. Lower pair is that kinematic pair wherein both the links have surface area of contact. So for example, a sliding pair, it has all its surfaces in contact. So it's lower pair. So basically every sliding pair is a lower pair. So now let's classify the kinematic pair on the basis of the closure. So what is closure? Closure actually means the way the links are actually attached together, so that it doesn't come off the contact. So there are two broad categories: self-closed and force-closed. Self-closed is something that where no force is required to keep all the links together in place, and force-closed, on the contrary, is the system where some external force is needed to keep the links together. That force can be either gravitational force, or that force can be either, you can say, spring force, or it can be any other force. So let's take an example of each of these. So you can take the example of a self-closed pair as any sliding pair. For example, that piston and cylinder. So the piston actually moves inside the cylinder, and that is a sliding pair, and no force is required to keep the piston inside the cylinder. So it is a self-closed pair. Now let's move on to force-closed pair. The best example is a cam and follower. So basically a cam actually raises the follower, and the gravity pulls it back down and keeps the cam and follower in contact. So it is actually a force-closed pair. So guys, now let's start with kinematic chain. What is a kinematic chain? Actually, if one end of a link is attached to the starting point of another link, it forms a kinematic chain. And if suppose that chain closes itself, it's called as a closed kinematic chain. So for example, if this is a link and its end point is attached to the starting point of another link, and this in turn is attached to the starting point of another link, and this thing is called as a kinematic chain. And if say there is another link that actually closes the chain, it is then called as a closed kinematic chain. Now let's move on to joint. Joint is the junction of two or more links. So if suppose it's a junction and there are two links attached, it will be called as a joint. And if suppose three links attached, then also it will be a joint. Now based on the number of links at this joint, we have divided this into three categories: binary joints, ternary joint, and quaternary joints. So if two links are attached, it will be called as binary joint. If three links are attached, it will be called as ternary joints. And if similarly four links are attached, it will be called as quaternary joints. Now we will learn to write ternary and quaternary joints as an equivalent of binary joints. So if suppose n links are attached at one joint, then we will consider it as equivalent of n minus 1 binary joint. Yes. So for example, let's take the example of binary joint. So a binary joint is a joint, is a system where two links are attached. So suppose two links are attached. So here n is equal to 2. So n is equal to 2, and n minus 1 will be 2 minus 1, that is equal to 1. So it obviously one binary joint. Now let's take the example of ternary joint. Three links are attached. So here it is 3 minus 1 is equal to 2 binary joints. So similarly, coordinate joint will be equal to 3 binary joints. So guys, now let's move on towards degree of freedom. So what is the degree of freedom? Degrees of freedom is basically the number of unique parameters that we require in order to constrain a motion of a system in order to turn it into a very useful machine. So in total we have 6 degrees of freedom. Now to calculate the degree of freedom of any system, we have this particular condition which is termed as the COURSEFAC criterion. Now it's nothing but n is equal to 3 into L minus 1 minus 2j minus h. Now the notations are n is equal to degrees of freedom, L is the number of links, j is the number of binary joints, h is the number of higher pairs. And now we will apply this kutzbach criterion to a very simple yet basic problem. Take this problem. In this, first we'll calculate the number of links. So number of links we'll start with 1. So it's first link, second link, third link, fourth link. So it's a hashed area. So obviously we can consider it as one single link. So it is fourth link, fifth link, sixth link, seventh link, eighth link. Now don't get confused when you see ground, because it is one single link. Don't consider it as like separate links. So it is one single link whenever you see some ground, because it's a single inertial frame. So here in our case L is equal to 8. So number of links is 8. Now let's see number of binary joints. So as you can recall from the previous topic, a ternary joint is equivalent to 2 binary joints. So first we will see how many binary joints we have and how many ternary joints we have. So in our case, we have taken each joint and we written in bracket the number of links attached to them, like which links are attached to them. So in first bracket I have considered this particular joint, and you can see 1, 2 and 3 links are attached. So I have written 1, 2, 3. Now in this joint 1 and 8 are attached, so 1, 8. You can do this, so it will be very simple and you will not get confused and not mix up. So you can see only one ternary joint is there. So this is equivalent to 2 binary joints, and rest all are binary joints. So it is equal to 1 binary joints. So in total we have 2 plus 3 and it's 5. So 9 binary joints. J is equal to 9. So in total we have 9 binary joints in this kind of system. Now let's calculate the number of higher pairs. So easily you can see from this that there is no such kinematic pair which is having point or line contact between them. So obviously h is equal to 0 in our case. Now let's put these values back into the equation. So we'll get n is equal to 3 into L minus 1, so it's 7, minus 2j, j is 9, minus h, that is 0. So n is equal to 21 minus 18, and that is equal to 3. So we have 3 degrees of freedom over here. Now this 3 implies that we have 3 unique parameters that we are going to need in order to constrain our motion of the kinematic system in order to turn it into a useful machine. So now move on to an extension of the kutzbach criterion, and that is known as the Grubner's condition. So what is basically Grubner's condition? Actually, we put some limiting conditions on this kutzbach criterion, and that is known as this Grubner's condition. So the limiting conditions are that n is equal to 1 and h is equal to 0. So basically we need a system where there is only 1 degree of freedom, hence we need only a single unique parameter in order to constrain the motion of the kinematic system in order to turn it into a useful machine. And we need h is equal to 0, so we are going to definitely need a system where there is no higher pairs. Putting these values back into the equation, we get 1 is equal to 3L minus 3 minus 2J is equal to 0, minus 0. So 3L minus 2J is equal to 4. This is known as the Grubner's condition. Thank you.